Hey coders, welcome back. So in the last video, we try this phone interview one from the Leetcode assessment section. So if you don't know, this is a great place to prepare and test your preparation basically. So we have like random sets, uh, and these questions are from like real company. So you can start, and there will be two, three questions randomly selected from the Leetcode problem set. And yeah, you can practice. So you can either choose online assessment or phone interview. So in my last video, I have chosen this phone interview one. So let's today choose this online assessment one. And before going, let me check my screen is visible. No? Yeah, it is visible. Sorry. So yeah, let's start with random question set from online assessment. Let's see. So there will be two questions. Generally, I think two medium questions are there in this OA. And in the I think phone interview also two questions, and in the like this one, in the on-site interview there will be three questions. I think EGM, one easy, one medium, and one hard. So yeah, let's go to the online assessment. See, we have 1 hour to complete all the questions. Two questions will be there. Yeah, let's start. Okay, so I think it's this is pretty standard question. A Fibonacci number commonly denoted by this, called the Fibonacci sequence, such that sum of the two preceding numbers are this. Calculate Fibonacci of n. So I think this is will be pretty easy if you know. It just need so generally in a dynamic programming problem, you have a recurrence relation, right? And if you know the recurrence relation, it is pretty easier. So basically, recurrence relation is something you are doing calculating something from the previous state, right? So here is the we already have this. So we can calculate Fn from n minus 1 and n minus 2, right? So that's the idea. So we can create a DP array for n plus 1, and we have to make sure we put DP of 0 equals to 0 and DP of 1 um, equals to 1. And then if n is less than, we can check like, okay, so what's the constraint for n? N can be from 0 to anywhere 30. So if n is equals to 0, we can, yeah, n is equals to 1, we can return n, right? So if it is n is equals to 0, the answer will be 0. If n is equals to 1, answer will be 1. And then for anything greater than 1, we can simply run the for loop from 2 to I less than equals to n. And then using this recurrence relation, we can calculate. So dp of I equals to dp of I minus 1 plus dp of I minus 2. And then you can simply return dp of n. So it's pretty standard, I think. Yeah, let's try submitting it. Okay, so what's the okay, I missed one thing. Sorry. So here, this condition should be on the top right. Um, yeah, this is a silly. These are the silly mistakes we should try to avoid. But let's submit it again. Yeah, it's submitted. You can also write a recursive DP if you wanted to. So I can show you all that also. Uh, yeah, let me comment out there. So the idea about recursive DP is, so we know that if n is equals to 0, we're gonna simply return 1, right? And then by this recursive method also, we can get the previous values. So like int previous is equals to dp of n minus 1, and the previous one and maybe previous 2 equals to dp of n minus 2, and we just need to return p1 plus p2, right? This is the base case, and for negative we also need to handle. So if the n goes negative, we have to return 0. And for n is equals to 0, it is also 0, right? Um, so, but we should try to get the answer from like the current state only. So, if it is going less than 0, then we're gonna return 0. If n is equals to 0, we're gonna return 0. And if n is equals to 1, we're gonna return 1. Right. So this is the way you can solve it using recursive DP. Now we just need to memorize this solution so we can create. Um, yeah, let me write this also. Actually. So yeah, so for example, if n is equals to 2, so we will call our method 1 and then we call for 0. So 1 will return 1 and the 0 1 returns 0 and then we're gonna doing this p1 plus p2. But this will give me TLE if I try to without. So let me, okay, I will do the same here also. If n is equals to 0 or n is equals to 1, we're gonna return 1. Otherwise, we're gonna return dp of n. And you will see that it will give me a TLE. So let me try submitting it. Okay, so for input 0, I'm getting this. Uh, okay, we have to return n. Sorry guys, my bad. Let's submit it. Okay, I'm getting success guys. Ideally, it should give me TLE, but constraint is pretty small. I think n is equal to 30. That's why. But still, if you wanted to, you should memorize this kind of problem. So how we can do that? You're gonna check what is the thing here in the changing in this my DP method. It is n that is changing, right? N is going from n minus one and n minus two. So we can create a DP array. So let me call it. I generally call my DP array as a memo, and then I'm gonna initialize this memo new integer of size n plus 1, right? So why this integer array wrapper type is because by default it will be null. If I use int, I have to initialize it something like minus 1 or some negative number or some very infinite number. But for memoization in Java, I generally use this wrapper type and you can use this. So now I created this memo. So what's the idea of catching? The very first step is you're gonna create this TP array. The second step, you're gonna add the one condition in the base condition along with the other conditions for this TP array. So I'm gonna say if my memo already have this value, right? So I'm gonna return it from memo instead of calculating it. So that's the first idea. That's the second step. Third step, you have to catch your answer. So this P1 plus P2 is the answer for n, right? So we can simply say this memo is equals to this answer. If I run this code, and now this is, yeah, it is getting submitted. Let's try submitting it. Yeah, it is 0 millisecond. Right. So this is how you can memorize it also from the recursive point of view. And what's the time complexity for this kind of problem is generally whatever your DP array, right? So we are not going to solve this problem recursively. And since we are doing this condition, now this will help make this time complexity linear because our memoization table is linear. So max to max, we will go to till this memoization only. Yeah, this is how we can solve this. What's recursive and iterative DP? Let's go to the next question. See, uh, okay, so this is the question. Let me check my screen once again. It is visible, no? Yes, it is visible. Okay. So Alice, okay, this Alice and Bob type of question generally I don't like it. It get messier, right? And generally, I see my constraint first. So 10 to the power 4. So we have to write the solution in linear and maybe n log n. Um, yeah. So let's try to understand this question. So we have Alice. Uh, she has n candies, where ith candy of type candy type I. Okay. Where the ith candy is of type candy I type. Okay. Alice noticed that she started to gain weight, so she visited a doctor. The doctor advises Alice to eat n by 2 of the candies she has. Right? And n is always going to be even. Alice likes her candies very much and she wants to eat the maximum number of different types of candies while still following the doctor's advice. So doctor says like you should eat only half of your candies. So what Alice is thinking, okay, since I have to only eat the half of the candy, why not I will try to eat maximum different types of candy, right? So given integer or a candy type of length n, return the maximum number of different types of candies she can eat if she can only eat the n by 2 of them. So for example here, so Alice has a candy type of 1, 2 and 3. Now Alice can only eat 3 candies. So since there are 3 types of candies, she can eat one of each type, right? So for example here Alice, so doctor says, so we have 6 candy. Doctor says like you can only eat 3 candies, right? So either she can eat this one, 1 and 2. So this will count as a 3. Let me highlight it. 1, 1 or 2 or like 2, 2, 3 or 3, 2, 1. Any 3 candies she can choose. Now, but what Alice wanted to do is she wanted to maximize, she wanted to taste maximum number of different types of candies, right? So this is the idea. Um, for example, here, uh, n is equals to 4. So the 4 by 2 is 2. So Alice can eat only 2 candies. Even though she can eat 2 candies, she cannot because there is only one flavor of candy. And it says like what is the maximum number of different types of candies she can eat, right? So this kind of whenever you see this maximum thing now, from my experience, uh, we generally have four different options. Let me whenever you see this maximization, something maximum, largest, right, or minimum, m- basically optimization problem. So for this now, I generally think of three, four algorithms. So the very first thing is DP, right? The second thing, generally in the minimization problem, is BFS. If you solve multiple different questions, you will see this. So DP, BFS, and of course there will be greedy. And the fourth one is binary search. So whenever you see this maximization kind of problem, na, try to solve different kind of problem, and you will see you can categorize those questions into these four parts. Right. So I'm saying this question, can I apply DP? I would say no. I'm not seeing any sub problem, overlapping sub problem, right? Can I apply BFS? No, it's not a minimization problem. So I will avoid that. Greedy can be, it can be possible. And the binary search, right? So if we have solved binary search on answer based questions, so this seems pretty similar. So there is a famous question like Coco eating banana, and then there is a very different kinds of problem for binary search and answer. You can search on the internet and try to understand it. So I will solve this question using binary search. It feels like binary search. And how I'm able to determine this? Just this logic. I have solved bunch of questions, and I can see this binary search fits pretty well in this types of problem, right? So let's try that. So I will call this A. So, so how binary search and answer works? Generally, what we're gonna do now, what we can think of, what is the maximum answer, what is the maximum number of answer it can have, right? And what is the minimum number of answer it can have. So I generally create two variables left. So minimum, I think if we go here, the candies is of even length, and candies will my array candy array will be minimum of size 2, right? So my answer will always be 1. In the worst case, Alice will be able to eat at least one candy. So this is my minimum. Now, what is my maximum? Maximum will be all the different types of candies in this my candy array, right? All the different kinds of candy. So either I can iterate over all these array and check how many different arrays, different numbers are there using set or map, whatever you are comfortable. I can just put just a higher, you can put higher bound as like 1e9, maybe integer at max value. That will also works. But, but simplicity, we can check like a dot length. Right here again, you can take either max value, whatever integer max along that max value, binary search will be able to tackle it, or you can calculate the manual. If you want to exact efficient solution, you should try to find should try to find number of unique candies, and that should be your ideal ride, right? And then we're gonna do typical binary search. My binary search is little bit different than you see in the internet. I will explain you how my this binary search works once we solve this problem. But it is typical. We're gonna create a mid, which so I do like this to avoid my bound condition, right? That overflow and all. Generally in the index-based question. So this way calculating mid always gives me a right way, so I don't have to think anything about it. So if you are also wanting to use, you can use this logic. Left plus right minus left by 2 instead of doing just left plus right by 2. And then I'm going to say, can this be my answer? So this is pretty predicate function. I will explain you this binary search logic in 1 second, but for now you can think like, is so mid is like my potential answer. So is mid my can be my potential answer? We're gonna check. If it is my potential answer, then I'm gonna say left is equals to mid, uh, else right is equals to mid. If this is my potential answer, then I should try to get a number higher than mid, right? If I'm able to, let's say we have hundreds of candies and we check, can Alice eat like 20 candies, 20 different candies? And we see from my good function, yeah, Alice is able to actually eat 20 candies. Then we should try to find anything that is bigger than 20. So that's what this condition is doing. And if we are not able to eat even the 20 candies, let's go below. Let's try for maybe 10, maybe 15, right? So that's the idea. And then I'm going to check return good of left a question mark left else left minus 1. Why I'm doing this, I will explain you also. But for now, I think you get this idea, right? How we are calculating this answer. And then let me try quickly write this good method, which is like a target. Um, and then this is my array. So this method's whole purpose is, can arrays eat these many target numbers of different candies or not? Right. So this is the expectation from this method. How I'm gonna do that is I'm gonna create a set of integer set new as set, right? Since Alice can only eat n by 2 chocolate, right? So I also need to make sure that. So I'm gonna say n is equals to a dot length, and then I'm gonna say for int um for int a of a, go to the each candies type and set dot add a, and if set dot size equals to n by 2, we're gonna break, and then I'm gonna say return set dot size is set dot size is greater than equals to n by 2 or not. Target. So let me explain you what this method is doing. So I'm saying, okay, so this is my expectation. Can Alice eat these many chocolates or not? Right. And then by doctor advice, she can only eat half of it. So whatever the A length, she can only eat n by 2 candy. That's right, correct? Now I'm going over each of these elements, each of the different candies. I'm adding this into my set, right? So one, two, three, three, four, four. All I'm adding, and then I'm making sure that this set size does not exceed by n by 2, because this is the limit. This is the hard limit she can eat, right? And then later I can just check whether the set size is greater than equals to target or not. So let's say see as a target, our method checks can see it 20 candies. And my set size is like 21, 20, if it 25 or 30, anything greater than target, that is good, right? She can eat. And if our set size is let's say 5 and the target is 20, she cannot. So this will return false. And by this false, it will come to this logic here. And if we and since it returns false, we try to reduce our bound, right? From left to right, we try to find something lesser than that, right? So that's the idea. I will explain you this binary search. Let me try to run this code once to see any compile time mistakes or not. And then I will explain you how my this binary search is pretty, I would say, solid implementation. It uses something called predicate. And yeah, I will explain you. Okay, so for this one, I'm getting three, right? Let's try submitting it. Yeah, I'm able to submit, guys. So yeah, we don't going to finish the session. I just wanted to give you a brief idea of how my this binary search is working and why I'm doing this line, right? This line, below line. So okay, let me quickly go through this. So how my binary search is working. So okay, so let's say you have some number 1, 2, 3, 4, 5, 6, 7 sorted number obviously because binary search you should have a sorted number and you wanted to find something that is equals to 5 or not. You want to basically check whether my number 5 exists or not based on my predicate logic, this method. So what predicate says is, so what's my predicate? My predicate says whether this is equals to target or not and target is my 5. So here if I come here, it is target 5? No. Is it 5? No. Is it 5? False. Is it 5? False. And then is it 5? True. And generally, when I do this kind of binary search, no, we don't do exactly. We do something like greater than equals to or less than equals to. So I'm saying let's try to find we are targeting 5, right? So let's try to find anything that is greater than equals to 5 or not. Right. So these are all not greater than equals to 5, but here at 5, I'm getting this 5. Okay, is it greater than equals to 5? Then it is greater than equals to 5, 6? Yes. Is it greater than equals to 5, 6? Yes. So this is the first idea you have to remember. So, and by this logic, where left less than right, and if it is a good, I'm saying left is equals to mid plus 1 and right is equals to mid, it's simply saying if I'm getting this here false, no, let's try to solve from here, right? And let's say if I'm at 7, since I'm getting this true, let's try to find something m- true in the left side. So generally, in my implementation of binary search, if you wanted to, you can see different implementation on the internet. The left one will always give me the very first true, right? So here in this predicate logic, what is the first left? The first left is this line, yeah. You see, first true as it index 5. This is my first. This is second true, right? So my left will always going to give me the first index where my predicate logic is correct. Right. So same thing here. So this good method is checking which is the can she can eat 20 candies, a she can eat 30 candies. If she can eat 30 candies, let's try to find something more, right? Something more. Maybe try with 40 candies, or maybe 50 candies. And then I'm changing this left and right. And this left will contain the first true. The first true where she can, I'm 100% sure she can eat that many a number of candies. But in this case, since I'm doing this left is equal to mid plus 1 and right is equal to mid, this generally actually I will get the scenario something like this true, 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 and then false, 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 right? Something like this. So I will get this true I will get here. This true. Uh, Let me highlight this. This true I will get. So sometimes what happens, let's say on this condition, if I'm checking, let's say my index is checking at this index, can elicit let's say here we have a value of 30 can see it 30 candies, right? So I will get okay can see it and this method will return true, correct? So my left now jump to here in this section in this FFFF section. So that's wrong now. So that's why I'm going to so it will return the very first false to me, right? So if I do something like this, left is equals to mid plus 1 instead of right is equals to mid. So this will give me the very first false. So basically I get always get either this false. So I am going to check whether this is correct or not. Can elicit these many candies or not. The very first step. If she cannot, well and good. If we can't, we just go just one below and return this as your answer. So yeah, that's the idea, guys. I hope you like it. Yeah, I'm quitting this recording. Thank you so much for watching. And let me know if you have any questions. Thank you.